Hi everyone, this is the lecture video for class 15 of PH 125, and today we're going to be continuing to talk about centripetal forces, and then we're going to get started talking about work. Okay, so just a quick review of the common forces that we've talked about so far in chapter 6. So we started with friction. Remember, friction is just the force between surfaces in contact, and it's a force that resists motion between those two surfaces. So we talked about two different types of friction. We talked about kinetic friction and static friction. So remember, kinetic friction is always equal to mu k times n, where mu k is the coefficient of kinetic friction. So whenever you have a kinetic friction problem, you'll probably want to start by finding the normal force. Okay. And then kinetic friction, it's always in the direction that opposes motion. All right, and then the static friction, force of static friction, it can take any value between 0 and some maximum force. That maximum force is the coefficient of static friction, mu s, multiplied by n. And the value of static friction then is determined by whatever force is needed to balance out the forces so that motion does not occur. Okay, and so then static friction acts in the direction that opposes motion that would occur if friction weren't present. So in these types of static friction problems, you always want to think about what would happen if there was no friction, if everything was on, something super slippery like ice or something like that, what would happen? And then whichever direction the object would slide, that's going to be the opposite to the direction of static friction. Okay. And so then after friction, we talked a little bit about the restoring force. This is the force exerted by a spring, and it's due to the fact that the spring has been either stretched from or compressed from its equilibrium position. And so then we said that F by a spring is equal to minus kx, where k is a spring constant, so this is a constant value that depends on the type of spring that you have, and x is the displacement of the spring from equilibrium. Usually when you have compression, we consider x to be in the minus x direction, and when we have a stretched spring, we usually consider x to be in the positive x direction. Okay, next up we talked about tension. So remember, tension is a pulling force that's transmitted by like a rope or a string or something like that, and it has constant magnitude everywhere in the rope or string, and its direction can be changed by a pulley, but its magnitude always remains constant. Okay, and then lastly, we talked about centripetal force. So centripetal force is any force that points towards the center of a circle. We learned that the centripetal acceleration for motion with constant speed v is always going to be v squared divided by r, where r is the radius of that circular motion. And so then the centripetal force, FCP, is going to be mass times the centripetal acceleration, in other words, mv squared over r. Okay, and just a quick reminder, all force problems you want to set up kind of the same way. So the net force acting, for example, in the x direction is equal to the mass of the object times the acceleration of that object in the x direction. And those two things multiplied together, mass times acceleration, are going to be equal to the sum of the forces acting on the object. And so you always have to be clear about the force acting on the object, not by the object. You'll want to do the sum of the x components considering directions of the forces. So are they acting in the positive or negative x direction? And then you can do the same thing in the y direction. So F net y is equal to the mass of the object times the net acceleration of the object in the y direction, and that's equal to the sum of the forces acting on the object in the y direction. Okay, so we're not really going to talk about anything new today with respect to centripetal force. This is just a quick reminder because we're going to do some practice problems in class working with centripetal force. So it turns out that the centripetal force, it's really, it's not like a new type of force. It's really just one of the old types of forces that we've talked about, but pulling the object towards the center of a circle. And so it can take the form of tension, for example, a ball on a rope here, and then it could also be gravity. For example, the satellite is held in orbit, in a circular orbit by gravity. In a washing machine, the normal force is what acts as the centripetal force pushing the clothes towards the center of the circle. And a really classic example that we're going to do in class is actually the centripetal force exerted by friction, for example, on a banked curve when you have a car on a road. Okay, So that really wraps up chapter 6. Like I mentioned, we're going to do some more centripetal force problems in class. But next up is chapter 7. We'll be dealing with work and energy. Okay, so chapter 7 is all about work and kinetic energy. And we're going to still need to use the net force acting on an object is equal to its mass times its net acceleration. You'll probably want to think about it in terms of x and y components again. So F net x is equal to ma net x, F net y is equal to ma net y. Okay, so that doesn't go away, but what we're going to be talking about this chapter are a few concepts of work and energy. So work specifically has the symbol W, which is why I was wary of using W for weight, because we use W for work. And what work really is the mechanical transfer of energy. So I'm warning you, these definitions are terrible. We're going to do a bit more work on the definitions a little bit down the road. Okay, energy, we use the symbol E, and it's the capacity for doing work. Like I said, these definitions are terrible. They don't really tell you anything. We're going to get there. We have to kind of unpack it. Work and energy are things that are like such fundamental principles in physics that they actually are really, really hard to define. But we will get there with some clearer definitions. Okay, so we have a few different types of energy that we'll be talking about in here. Kinetic energy, K. This is the energy of motion. Potential energy is stored energy, and there are a few different types of stored energy that we'll be talking about. For example, gravitational and potential energy due to a spring. Heat is another type of energy. It's really the transfer of energy from a hot object to a cold object. And it turns out that mass is another type of energy. E is equal to mc squared. This is Einstein's famous equation. Okay. So it turns out that energy can be transferred and changed between these different types, and there are other types as well, but total energy in the universe is always going to be conserved. Okay. Yes, and as I mentioned, those definitions are terrible. We'll get there. Okay, last thing on our list for just brief introductory information here, we'll also be talking about power this chapter. So power has the symbol P, and it's just the rate at which work is done. Let's talk a little bit more about work then. So we're going to start with work done by a constant force. So remember, work is the mechanical transfer of energy, but more specifically, we can say that a force does work on an object if that force acting on the object causes that object to have a displacement. Okay, and so specifically then, work is equal to F d cosine of theta. So F is the force acting on the object, and in this case, it's a constant force. D is the displacement of the object, and theta is the angle between D and F. Okay, so work has units, we call them joules. Looking at Fd cosine theta, I know that force has units of newtons, D has units of meters, and so then a joule is really going to be a newton times a meter. Breaking it down into SI units, a newton is a kilogram meters per second squared, and so then a joule is really going to be a kilogram meters squared per second squared. All right. So like I mentioned, the angle theta is really the angle between F and D, and so the way you can find the angle theta is by arranging the vectors D, which is the displacement, and F, so that they are tail to tail. And then they're like the arrows point away from each other, right? So if you arrange them tail to tail, then the angle between them is going to be the angle theta that you need in this equation. So I have a few examples here. The first example, I have F is my blue vector and D is going to be the green vector here. And so as you can see, I've arranged them so that D and F have their tails together. In other words, they're tail to tail. And so then the angle theta is going to be the angle between F and D. Okay, and so another way to think about Fd cosine theta is to consider F cosine theta to be the component of F that's in the direction of the displacement D. So as you can see here, if I were to think about a right triangle, it would have an angle theta here. And so the component that's adjacent to the angle theta would be the component that's in the same direction as D, and that's going to be F cosine of theta, right? So it would be the component that's parallel to the direction D here. Okay, so let's do one more example. So here I have D pointing directly to the right, and F is kind of upwards and left. So again, I've ranged them tail to tail, and then I've drawn the angle theta in between them. Okay, and so here then it turns out that F cosine theta is really going to be the component of F that's parallel to D, but really it's going to be pointing in the opposite direction here, right? So you would end up getting F cosine theta pointing in the negative x direction, whereas D is pointing in the positive x direction, but it's still this component in here that's parallel to D. Okay. Last example, I have everything tilty here. So if D is tilted, then I still can arrange F and D so that they're tail to tail. Theta is the angle between them. F cosine theta, again, it's just going to be the component of F that's in the same direction as D. Now let's talk a little bit about the sign of work. Is it positive, is it negative, or is there no work done? Okay, so we have a few special cases here. The first case is when theta is equal to 0. So remember, theta is the angle between F and D when you have them arranged tail to tail. And so if they both point in exactly the same direction, then I would say that theta is going to be 0. There's no angle between them here. Okay, and so in other words, all of F is in the same direction as D. All right, and so in this case, I would just get F times D because cosine of 0 degrees is 1. And so I would end up with work being a positive value. F and D are both always magnitudes here. And so I would end up with a positive value because I have positive F times positive D. All right, what if I have theta equal to either 90 degrees or negative 90 degrees? So in this case, I have F pointing straight perpendicular to D, right? And so what that means is the component of F parallel to D, it must be 0, right? Because for example, here I have F pointing directly in the Y direction, D pointing directly in the X direction. And so there is no component of F parallel to D. In other words, you can think about the angle between them here. This angle theta is going to be that 90 degrees. Cosine of 90 is 0, and so there's no work done whenever you have force perpendicular to the displacement of your object. Okay, so a really common example of this is the work done by the normal force on an object that's moving parallel to a surface. So that normal force always acts perpendicular to the surface, and if your object is moving along the surface, then those two things, the displacement and the force, are always going to be perpendicular to each other. And so the normal force does not do any work when the object is moving parallel to the surface. Okay, last example here for our special cases. What if the angle between F and D is 180 degrees? And so this would be the case where we would say that's like anti-parallel. So they both are along the x direction, but D is in the positive x direction and F is in the minus x direction. And so I would say that they're anti-parallel here. And so whenever the force and the distance or displacement of your object point in opposite directions, complete opposite directions, this is the case where work is negative. And we can see that because cosine of 180 degrees, if you try plugging it into your calculator, you should get -1. And so you just get F cosine of 180 is just negative F. And so you end up with work is equal to minus F times D. And so in that case, then we get negative work. All right, so what if we're in between these cases? Well, so if the angle between F and D is something between -90 and 90, so in other words, the force and the displacement, the two vectors, they generally point in the same direction, then I would say that the work done is always going to be positive. If instead, the angle between F and D is between 90 and 270, so they generally point in opposite directions, then the work is going to be negative. Okay, so let's do a practice problem here. As part of a workout, you're holding a plank. In terms of your mass and the length of your arms, we want to know how much work do you do on the floor while holding plank. Okay, so let's see how I answered this question. So in this case, you are stationary, the floor is stationary, which means that there's no displacement happening, right? And so since D is 0, work done has to be 0 as well, right? So work is going to be FD cosine of theta. D is 0, and so work is also 0. So I would say answer C here. So it doesn't matter how much of a force you're exerting on the floor, the work is going to be 0 if the displacement is 0. All right, let's do one more. So now let's think about push-ups. And so when you do a push-up, we want to know, is the work done positive, negative, or 0? And think about the case both for pushing up and for lowering down. So the trick to this one is realizing what is the displacement of the floor relative to your nose as you are pushing down or pushing up. Okay, so let's see about this case. So what I would say is that as you are pushing down or as you are, as you're like lowering down or as you're pushing up, in both cases, the force that you exert on the floor is going to be downwards, right? So you're always pushing down on the floor. Okay, so then the key is just to think about what is the displacement of the floor relative to you as you lower down versus as you push up. So since I listed up first, let's do that one first. So as you push up, the floor looks like it's going away from you. It looks like it's actually going downwards. So I would say that your displacement is downwards, and so is your force. And so I would say that you have positive work being done then, because the displacement is down, the force is down, they're parallel, and so you have positive work. If instead you're lowering down, then the floor is like coming up to you. So that would mean that the displacement of the floor relative to your nose would be upwards, whereas you're pushing downwards, and so the work would be negative. Okay, and so that tells me that I would select answer A here. All right, and so this was the work done by a single force, is FD cosine of theta. But what if we have the work done by multiple forces? We want to know what's the total work done by multiple forces. Well, in that case, we have a few different ways that we can calculate it, but the general idea is that the total work is going to be the sum of the work done by each force. So I can just split up my work equation into each of the forces acting on my object. So for example here, if I have forces 1 and 2 acting on my object, I would think, what is my force 1? What is the angle between force 1 and the displacement of the object? And then I would calculate the work done by that first force, right? So this term here is going to be work 1. Okay, and then I could also think about what is the second force, what's the angle between the second force and the displacement. Then F2 cosine theta 2 times the displacement would be the work done by the second force. And you could just add them up. The next way you can think about it is by noticing that you have F1 cosine theta 1 plus F2 cosine theta 2 all multiplied by D. And so it turns out that this is really going to be the net force multiplied by cosine of theta, which is the angle between the net force and D. So those are our two options for calculating the total work done by multiple forces. So let's look at the two options in more detail here. So I have a box, say F1 is pushing downwards and to the right and F2 is pushing to the left, and the displacement of the box is going to be to the right. Okay, so approach 1 is just to find the components of each force along the direction of the displacement, so along D, and then you add the components together and multiply by D to get the total work. So here I would look at my force 1, which is this orange vector here. D is horizontal, and so I would draw the angle placing F1 and D tail to tail and get theta 1. Then I could multiply F1 times cosine of theta 1 to get the component of the force along D. I can do the same thing for F2, so F2 is pointing directly to the left, whereas D is pointing directly to the right. So here theta 2 would really be 180 degrees. I would get something that's like F2 times minus 1, right? So that's going to be F2 cosine of theta 2. And then we would want to multiply that by D to get the work done by force 2. And then you can just add the forces together. So I would get F1 cosine theta 1 plus F2 cosine theta 2. If you add them together, you get the net force acting on the box in the direction of the displacement. So that would be F1 cosine theta 1 plus F2 cosine theta 2. And then you just multiply by D to get the total work done. Okay, let's look at the second approach, which is using the net force. So they're really equivalent. It's totally up to your preference. But the approach 2 here is just to find F net first and then find the angle between your net force and D to calculate the total work done. Okay, so here I have my same two forces. I have F1 downwards and to the right, and I have F2 pointing to the left. And so I could add them together. I would want to use vector components to add them together, right? So I would want to find F1x plus F1y, and then F2 really only has an x component here. I would want to add those together, and that would give me the net force. Okay, and so then I would think about what is the angle between the net force and my displacement. And so here I've drawn in the angle between the net force and the displacement D, and then the component of the net force along D is just going to be F net cosine of that angle between them. Okay, and so then the total work done would just be F net cosine theta times D in this case. All right, so last sort of topic for today is the graphical interpretation of work. So we're going to start by thinking about a constant force. So whenever you have a constant force, if you were to plot force versus position, you would just get a horizontal line, right? Because the force is constant in position specifically. All right, so force versus position curve, you would just get this horizontal line here. And so then I would say that the height of that force, the height of that curve off of the position axis here, would have a height of F, right? That's the magnitude of the force. Then the displacement would be the difference between the initial and final positions on the graph. And so here I have x final and x initial marked in, and so my displacement would be the distance between those two, x final minus x initial. Okay, and so then I remember in the case where I have, and I'm assuming that the force and the displacement are in the same direction here. So in that specific case, I would find that work would just be equal to F times D. And so really then, if I think about this rectangle that I've shaded out here, that rectangle has an area of F, right, because that's the height of the rectangle, times D, which is the width of the rectangle. And so really then the area under that curve between my final and initial positions is equal to the work done by that force. And so then I find that work is really the area under a force versus displacement plot. Okay. And so then this is true in the case where we have a constant force, but in general, you won't always have a constant force. You can have a force that varies with position, but in that case, the work done is still going to be the area under the force versus displacement curve. So let's think about some forces that might vary with position. So one we've already talked about, remember we talked about the restoring force of a spring. We learned that the force exerted by a spring is equal to minus kx. Remember, x is the displacement of the spring from its equilibrium position. And so then we also know that there's this Newton's third law pair here. So the force exerted by the spring is equal and opposite to the force on the spring. And so the force on the spring is just going to be plus kx. All right, so that would be like the force you exert when you either stretch or compress the spring, versus F by the spring, which is the force that the spring itself exerts. Okay, another example is the force of gravity. In here we always just talk about force of gravity being equal to the mass of the object times the acceleration due to gravity g. But realistically, g is going to be dependent on location. So if you get really far away from the Earth, then it turns out that force is dependent on position. And so then you would really need to think about work being done by gravity as a work being done by a variable force. In other words, a force that depends on position. Okay, so like I mentioned, the graphical interpretation is still true. Work is just going to be equal to the force under an F versus D plot. So in these specific cases where we have work that's done by a variable force, you wouldn't be able to use work is equal to FD or FD cosine theta. That's only for the specific case where F doesn't depend on D. So mostly in here we'll be dealing with constant forces, so you'll be able to use work equals FD cosine theta. But in this specific case of the spring, you will have to think about work done by a variable force, and so then you would not be thinking about FD cosine theta. Okay, let's look at another example of work that depends on position. So when we have here, I have called it just it's a piecewise constant force. So what if you just got a plot a force versus position that's just little pieces of constant force, basically. Then you could calculate the total work done by this piecewise constant force by just calculating the area under this curve. All right, so that's like a non-specific example. Basically, the only example that we'll be working with in this class is the work done either by a spring or on a spring. So let's start with the work done on a spring. The work is still just the area under the F versus D plot. And so here we remember that the work done on a spring is equal to Kx, right? So this is the force that you would have to exert on the spring to either stretch it or compress it. Okay, and so now to think about the work done, we would think about a force versus position curve. So for example, if you stretch a spring from equilibrium, you would be exerting a force in the positive x direction, you'd be stretching it, and you'd be displacing the spring also in the positive x direction. So here my force is this orange curve here. It's going to be directly proportional to the position of the spring relative to its equilibrium position, so how much it's been stretched, which is a positive x value. Okay, so it's just this vertical line. It has a slope of k, right? That's that spring constant. And so then I could calculate the work done on a spring as you stretch it to position x by just calculating the area under this curve. It's a triangle, right? It's a right triangle, and so I could use 1/2 base, which is going to be x, times height, which is going to be f. F is really kx, and so you get 1/2 x times kx, which is 1/2 kx squared. Okay, and so this is the work done on a spring. It's always 1/2 kx squared, and it turns out it's always going to be positive because no matter what, when you displace a spring from equilibrium, you're always going to be pushing or pulling on it in the same direction that it's displaced from equilibrium. So this case, it was stretching a spring. If instead you were thinking about compressing a spring, then you'd be pushing a spring in the negative x direction, and it would also be displaced in the negative x direction. You'd end up with two negatives multiplied together, and you'd get a positive. So this work done is always going to be positive. I don't recommend memorizing that. I just recommend memorizing the fact that work done by a force that's parallel to a displacement is positive. If they're anti-parallel, it's negative. That's much easier to remember than the individual specific cases. Okay, and that's because next up we're going to talk about work done by a spring. And so for work done by a spring, it turns out it's still 1/2 kx squared, but it can be positive or negative. And that's because the force exerted by a spring is F equals minus kx. But in this case, you could have a force that's parallel or anti-parallel to the direction of motion or the displacement of the spring. So for example, if you have a stretched spring and it's moving in the positive x direction, so it's stretched and it's moving past its equilibrium point, then what would end up happening is you would have the force exerted by the spring acting in the negative x direction, but its moving or its displacement is in the positive x direction. And so you would have 1/2 the base, positive x, times the height, which is negative kx, and so you would end up with minus 1/2 kx squared. All right, what if instead your spring had been stretched past equilibrium, but now it was moving in the negative x direction? So it had been stretched past equilibrium, but now it's moving back towards equilibrium. Well, in that case, the force is still going to be pulling it back towards equilibrium, which is going to be in the negative x direction. And it's also moving, so its displacement is also in that negative x direction. And so what that means is you get two minus signs, they cancel, and you have just 1/2 kx squared. So for this one, it's really important when you have work done by a spring to just remember to think about, is my force parallel or anti-parallel to the direction of motion of the spring? Okay, so here's some examples working with that. So you push a block attached to a spring until it's compressed. It's compressed by a distance x from its equilibrium position, and then you release it. Okay, and so we want to know, is the work done by the spring? So we're going to be thinking about the force exerted by the spring then. So is that work done as it pushes the block towards equilibrium? Is it positive, negative, or zero? And here I recommend that you sketch it out or think it out. Is the direction of the force exerted by the spring, is it the same or opposite to the direction of the displacement of the spring? Okay, so here's a little sketch. You exerted a force, that's this black arrow here, that caused the displacement of the spring in the negative x direction, but from equilibrium, right? So it's pushing in the negative x direction. Then you release the spring. Okay, so now we've released the spring. The force exerted by the spring is always pushing back towards equilibrium. So here that's going to be in the positive x direction. And once the spring is released, the block and the spring are both going to move in the positive x direction. So the displacement is also going to be in the positive x direction. So since the force and the displacement are parallel, I would say the work done is going to be positive here. So that's answer A. All right, let's try one more. This is the same case, right? The block has been compressed and it's moving, but now it goes past its equilibrium position. And we want to know now, is the work done by the spring going to be positive, negative, or 0? And again, I would recommend sketching it out. Okay, so here's my little sketch drawing here. So I have our first two situations, right? It's been compressed, and then as the spring will push it back towards equilibrium, but it overshoots. And so it will go past equilibrium. After the spring passes through equilibrium, it's going to be pulling back on the block, right? It always wants to pull towards equilibrium. And so it's going to start pulling backwards on the block. And then the block, though, is still moving forward. It's still moving in the positive x direction. So now I have a force that's in the opposite direction compared to the displacement of the spring. And so I would say that the work is going to be negative. In other words, the angle between them is 180 degrees, right? So you end up with that negative sign. Okay, all right, so that's it for today. We'll be doing some practice problems, like I mentioned, with centripetal force, and then we'll also do some practice problems with work in class. So I will see you then.